So, hello everyone. I will start this talk by giving a bit of background in group theory. One of the most important results of group theory is the classification of finite simple groups. And the classification of finite simple groups states that every finite simple group can be classified in either one of 18 different infinite families, such as the cyclic groups of prime order, the alternating groups with n bigger than or equal to 5. But apart from these 18 different families, there are also 26 sporadic groups. And one of these sporadic groups is the group of interest that we'll talk about in this talk today. And that group is going to be the Mathieu group 24. And for this Mathieu group 24, it's a very interesting group. And to study it, Rob Curtis, back in 1976, developed a very special tool, a very special diagram called the miracle Octad Generator. And this diagram is what I will be discussing today. So we'll start with a bit of information on Steiner systems. So first I will give the definition of a Steiner system. So Steiner SDBN system, where t, b, and n are all integers, where t is greater than 1, is greater than t, and n is greater than b. Such a Steiner system is a pair SV, where firstly S is just a set of n elements. Second, B is a collection of subsets of n. Of subsets S. And these subsets will all have to be of size B. And we will call these subsets blocks. And then the third and final criteria that we have is that for every subset, of S with exactly t elements, we will ask that any such subset is contained in exactly one block. And to make this definition a bit clearer, I will give a small little example. This example is the family plane, as some of you might know it. And so this is a specific example of a Steiner system. In this case, our set of n elements will be the set of points. So in this case, it's the set of points. The blocks that we will have, or a collection of elements of size V, will be the lines that go through the points. And our last criterion is every subset of S with exactly two elements. So for every line that has exactly 2 points, there's exactly one unique line that goes through every 2 points in this system. So the third criterion here is actually satisfied. And so this is an S2, 3, 7 system. Now for the Steiner system, one may ask if we can determine a priori what the amount of blocks will be that the system has, because it's not specified anywhere. And we actually can. So lemma. Suppose we have a Steiner S in the system, then the amount of blocks we'll call B will be equal to n choose T divided by B choose T. And the proof of this is not really that difficult. It's just a relatively straightforward counting argument. We will count the amount of subsets of S with exactly T elements. And so we can do this in two different ways. We know that S is a subset with n elements. So one of the ways that we can do is just n choose 2 by definition. N choose T. Sorry. And then the second way we can do is our third criterion of the Steiner system says that for every subset of T of S with T elements in it, it's contained in exactly one block. So if we just take all of the blocks and all of the subsets of the elements inside of the blocks, then this will also have to be equal. Then this is most of the important stuff surrounding the Steiner systems. But I will note one more thing. These parameters, T, B, and S, we can just mostly choose them, apart from there's the restraint that T has to be smaller than B, has to be smaller than S. But when we ask if for any choice of T, B, and S, if a Steiner system actually exists, and the answer to this will be no. We can actually find specific choices of T, B, and S for T, B, and N for which the Steiner system doesn't exist. And one such system is actually the Steiner system 2, 3, 8, or well, the Steiner system because it doesn't exist, but these parameters. And a really easy way to see it is with the lemma we specified above. Because if we plug this in, we will get that the amount of blocks will be equal to, in this case, 8 times 7 divided by 6. But this will not be an integer. And the amount of blocks always has to be an integer. So this doesn't work. Another question maybe is that if we choose some T, B, and N for which a Steiner system actually does exist, is it unique at isomorphism? And again, the answer will be no. There are multiple possibilities, but it's a bit more difficult to show it, so I will just state that the Steiner system S2, 3, 13, S2 candidates to isomorphism. So that's yeah.
Do you mean by isomorphism purely on the set of elements, like an isomorphism, or is there?
Yeah, just by relabeling the elements and yeah. Oh, maybe one more thing that I should mention. In the introduction, I was talking about the Mathieu group M24. The way that this Mathieu group is defined is actually as the automorphism group of the Steiner system is 5, 8, 24. So in light of these two things, it's probably important to state that this system actually does exist. And also, if we find some system, then it's going to be unique up to n isomorphism. So if we have any other 5, 8, 24 system, it's going to be isomorphic to the one that we are going to construct in this talk. And the automorphism group here is just that if we have it's a subset of symmetry group with 24 elements, and it has to send any block to any other block. So now, in the handout that I have given you, there's now a small little section on the Golay code. I'm going to skip this section because of time reasons, but it's not that important to the proof. We will, at the end of the talk, we will come back to it, but you can skip it for now. So we'll go on to the section about the hexacode. So maybe a bit of notation to start. We will denote F4 with the Galois field of 4 elements. So this is just F2x with x squared plus x plus 1 divided. Which is just this. I'm pretty much just interested in these elements and not exactly their relations between the elements. So just to write it a bit shorter, I will just let x be omega and let x plus 1 be omega prime. The relations are all still satisfied. These are just exactly the same thing, but it will make my life a little easier by writing down the following few statements. So, we will now define the hexacode. I have given a few definitions in the notes. There is only one definition that I will be interested in here today. The other two are more commonly regarded as the definition of the hexacode, and this is pretty much a lemma, but it's all equivalent, so it doesn't really matter. So, X56 is the linear subspace of the 6-dimensional vector space over the Galois field F4, and we'll say that the code words A, B, C, D, E, F, where all of these elements are just elements of our Galois field F4, is an element of the hexacode. If and only if it satisfies the following 3 rules. So the first rule is called the 1 rule, and it states that A plus B has to be equal to C plus D, which has to be equal to E plus F. And all these things have to be equal, and we're going to give this element a name, and we're going to call it S. The second rule that it has to satisfy is called the omega rule. And the omega rule states that A plus C plus E will have to be A plus D plus F. This will also have to be equal to B plus C plus F, which is also equal to B plus B plus D plus E, if I'm correct.
Yes.
I don't try to get it wrong, but perfect. And all of this, if we have called this element S, this is going to have to be equal to omega S. So from there, the names, the 1 rule, because it has to be equal to 1 times S, the omega rule, because it has to be equal to omega times S. Similarly, we are also going to have the omega R rule. And this is just that B plus D plus F. So we just kind of take the complements of the above things. So it has to be equal to B plus C plus E. So it has to be equal to A plus D plus E. this is going to have to be A plus C plus F. And this is going to be equal to omega bar times S. So if these three very restrictive statements are all satisfied, then we have a code word that is in hexacode. Yeah?
You mean by S? I didn't see where the S comes in. So do you mean the S is the same in these three?
Yes,
things?
in all of
Okay,
these
for
three
one,
things, yes, it's the
This is
same.
defined as
Exactly.
equals B.
So now, with the definition of the hexacode, we will solve a few problems. So, this proposition, and this is often called the tree problem. We have a code words of our hexacode: A, B, C, D, E, F. And we don't know all of them, but we do have 3 known digits that are all definitely correct. 3 known digits. We can complete it. And we can also do this uniquely. For this theorem, I could give the general proof, but I'm just going to do this with an example. But every single step should be clear, and it should also be clear that this works for every single code word. So the example that I'm going to use is the code word omega. We don't know the second element. Then 1. We don't know the fourth element. And 0. And we also don't know the last element. So first, we know that this is an element of our hexacode. So all of these properties have to be satisfied. And in particular, the one rule is most of the time the most restrictive one. If we had a code word which had a pair of these elements, we could immediately calculate S. And then if we had S, we could use the omega rule and the omega bar rule to find all of the other elements pretty easily. But if we don't have this one rule, if we cannot find this S, such as in this example, what we can do is we can look at the omega rule and the omega bar rule, and we have one of these 8 equations for which we know all 3 of the digits. So in this case, it's going to be A plus C plus E. So by the omega rule, omega plus 1 plus 0 is going to have to be equal to omega times S. And this is omega bar, this is omega times S. And from this follows that S will have to be equal to omega. But now we know S. And we know from all of these 3 pairs, exactly one of the digits, we know S. So now we just solve this very small system of equations. And if we do that, then we find that B has to be equal to 0. D has to be equal to omega bar. And F has to be equal to omega, if I'm not mistaken. Yes, exactly. And we can solve this code word as omega 0, 1, omega bar 0, and omega. And you can check that this is again in hexacode. So this is pretty much how we solve the tree problem. If we have a code word, any 3 given digits, we can just complete the code word to a code word in hexacode. Very similarly to the tree problem, we also have another problem. This is going to be the 5 problem. And it's going to be exactly the same. If we have A, B, C, D, E, F. A code word with 5 known digits. Then, of course, by the 3-4 rule, we can very easily complete this. But we'll add the extra condition that one of these known digits may be wrong, actually. So it's potentially one wrong. Then we can complete it again uniquely. And to do this, I will again show it with an example. The proof is extremely similar in the general case, but it will just be a lot easier to follow. So, example, see what I used here. So we will consider code word omega 1, 0, omega 1, and we don't know the last digits. So in this case, just to be clear, one of these digits could be wrong, and we will have to correct this rest of these. So again, we know that this code word has to be over hexacode, so we will look at the one rule again. And in the one rule, we can see that of AB, of CD, and of EF, we actually have already 2 pairs. And if we check those 2 pairs, so in this case, omega plus 1 and 0 plus omega, we'll find that the first one evaluates to omega bar, and second one evaluates to omega. But this will have to be the same. So we actually already know that we do have a mistake, and that the mistake is in either one of those. So what we'll do now is we're going to just forget one of them. So we will look at, for example, omega 1, question mark, 1 question mark. And this is just a tree problem. So I will, again, not completely solve it. I think that I have given the solution here somewhere. Find it, yes. So if we solve this problem, then we will get that this is equal to omega bar, F will have to be equal to omega, C will have to be equal to omega, and D will have to be equal to omega bar. But from the vector that we do have, we actually see that C is not equal to omega, so this could be the mistake, but this is actually also not equal to omega bar. So this cannot be the case, because we cannot have 2 mistakes. So from now, we know that the mistake is actually set in the first pair. So what we do now is we just forget the first pair. And this is again another free problem. And we can again just solve this. So if we solve this, we get that A is equal to omega, B will have to be equal to 0, and F is equal to omega bar. And here this does work, because A actually is in fact equal to omega, and we can see that the mistake here is that B had to be 0 and not 1. So we can complete this to the code word omega 0, 0 omega, 1 omega bar. So this is the section about hexacode. The most important part is if we have a hexacode word with 3 known digits, then we can complete it. And if we have a hexacode word with 5 known digits, maybe one of them being wrong, we can also complete it. And this will be what we're going to use in the next section of the important section.
So this says that the dimension of this C6, so C6 is a subspace of a 6-dimensional vector space.
Yes.
With F4.
Yes, a
And we are
3-dimensional.
showing that it's 3-dimensional.
Yes, exactly. This is not a proof in any way or so, but it will be the case.
Yeah.
So, where's the
So one actually only needs 3 conditions to define it, as opposed to all these 1, 2, and 3 rules.
Yes,
But
yes, exactly. Perfect. So now for the most important section, the numerical Octad generator, or what I will call it from now on, MOG for short, because it's a pretty long sentence. What we will consider now is a 6x4 array. 6 elements here, 4 elements here. And we will, for simplicity's sake, split it up into small little blocks of 2x2. And this will be a subspace of the 24-dimensional vector space with elements in F2. So for example, we can 0 here, 1 here, 1 here, 0 here, and so on. That's going to be a lot to write down every single time. So instead of doing that, I will just, if there's a 1, I will place a star, and if there's 0, I will place nothing. So we have an entire subspace of these collections of diagrams, and we want to place some restrictions on them. The first restriction is going to be that every single column of the subspace, so every single one of the 6 columns, is going to have the same parity. So for example, if the first column has 1 star, then all of the other columns also have to have an odd amount of stars. So either 1 or 3. And exactly the same for even, of course. And the second criterion is very similarly, the top row of this diagram, so this row right here, has to share the same parity. And if these 2 conditions are fulfilled, then we say that our diagram right here is a position of the miracle Octad generator, of the MOG. So if these 2 are fulfilled, then we have a MOG position. And now, since we are studying the columns already for the parity, what I will do is for every single possible column, I will define a function that takes a column and sends it to an element of the Golay field F4. So, for example, we have these 4 columns. One possibility is that there's a star in the top element, or these are in the bottom 3 elements. Those are odd columns. Another possibility is the column with no stars, and the possibility of all possible stars. These are, of course, even columns. and we'll evaluate all of these columns to 0. And we'll do the exact same thing for every other element. And I will write all of them down because this is a pretty important part of the mock. For 1, omega, omega. So for 1, these are the odd positions, and these are the evens. And for omega, let's start right here. These are all the possibilities in the omega bar. So for every possible column, we associate a number, or well, an element of the Golay field to it. And if we apply this sort of column enumeration to our mock, take for example the following, where we have star right here, star right here. Here. We can also evaluate this mock in exactly the same way as mock. We just do the same for every column. So this column is going to be omega. This column is going to be 0 because it's empty. There's empty. There's omega again. This column is going to be 1. And this column is going to be omega bar. And we check that this is a valid position because every column has even parity, and the top row as well. And now right here, we have a word of 6 elements of the Golay field. So it may be a reasonable question to ask if this is an element of our hexacode. And in this case, it will be. And specifically, this is the definition. If we apply this scoring to any mock position, and the resulting code that we get is an element of the hexacode, so if we for the mock position and the resulting score is an element of our hexacode, then we will say that this mock position that gives us the scoring, so the mock position, will be an element of the Golay code G24, the extended Golay code. And many of you who know the Golay code may ask, like, why? Why is this the same? This is, I mean, it is a two-dimensional subspace, but what does the stars have to do with anything? Why is this evaluation with the Golay code? Code is the same. I will explain all this at the end of the talk. But for now, just go along with it. So, with the definition of the Golay code 24, we can define one more thing before we can get to the big theorem. This diagram, for example, it has 8 stars in it, and that is going to be the definition. If a diagram of the Golay code has 8 stars, so some element X for G24 has 8 stars, we call X on top of that an Antwerp theorem. The octad 324 for my S, 5, 8, 24 Steiner system. The proof is going to take a bit long if I have covered it in all of its generality. So again, I will just give a few examples, but these examples will hopefully again be enough to convince you that this is actually the case. So what are the criteria that we have to satisfy to be a Steiner 5A24 system? Well, we have to have a set of 24 elements. We do, just the 24 elements in our diagram. We have to have a collection of blocks. And again, we do. These are going to be the octets. So all that we have to check is the final condition. And the final condition, if it's still on the board, I think I deleted it. But if we have a subset of 5 elements, so just a diagram with just 5 stars placed anywhere in the diagram. So there, for example, it doesn't really matter. Then we would be able to complete it uniquely to one of these octets, 2 elements in here with 8 stars, with scores that evaluate to the C6 word, and it has to be a valid mock position, so the parity has to be the same in every column and in the top row. To do this, I will make one observation. If we place 5 stars in such a grid, then we have a few different cases. So if you look at the columns, a first possible case is that we have 4 stars in a single column, 1 star somewhere else, and 0 stars everywhere else. Another possibility is that we have 3 stars in a column, 2 stars somewhere else, and again, zeros. 3, 1, 1, zeros, 2, 2, 1, with zeros, 2, 1, 1, 1, with zeros, and then all ones, and then a 0. And these are all the possible column distributions. But all of these column distributions fall in exactly 2 cases. The first case is that 5 of our columns have the same parity. And this is going to be the case here, 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 and so if you check, 5 of the columns either have an even or not parity. In the remaining 2 cases, we have 3 evens and 3 odd columns. And for the sake of brevity, I won't show all of the possible cases I can, but I will just show a few examples right now. If we have this first case, that 5 of the columns have to have the same parity, you will always notice the other column does not share that parity. So we have 3 stars to place in our entire grid. We already know one of those stars has to be in that final column, because otherwise the parity constraint would not be met. So I will give the example that I've written down here. So case 1. Right. We have 5 columns that are even, 1 column that's odd. If we evaluate the score on this, we will get omega 0, 0. We know that in this column, we do again have to place a star somewhere. So we didn't exactly know what this is going to be. And here we have 1, and here we have 0. This might look suspiciously familiar to some of you. And notice that we also have two remaining stars that we have to place. Both of those stars will have to be in the same column, because otherwise the parity constraint is not met. And this is just a 5 problem. We know that one of the stars has to be in this column that has the wrong parity. And we know that in one of the other columns, we also place the two remaining stars. The fact that this always works uniquely and that we always have a solution is not immediately obvious, but because of time constraint, I wouldn't be covering this. So here, in case 1, we just solve a 5 problem and we're done. This works. In case 2, so in this case, we have 3 evens and 3 odds. If we look at the scores of these, we will get that this is 0, this is omega bar, this is 0, this is omega, this is 1, and this is 0. Now we have to place 3 stars. But coincidentally, we have 3 columns that are even and 3 columns that are odd. So the parity has to be one of the two. So either we have to place the 3 stars all in different odd columns, or we have to place the 3 stars all in different even columns. So what if we just, for the even columns, for example, suppose we have to place the 3 stars in even columns, and then this is just a 3 problem. Or we can do exactly the same thing with the odd columns. Question mark omega bar. 0, 0. And again, it will turn out one of these three problems is going to be impossible because of the stars that we already have. It's not immediately obvious why, of course, but you could just trust me on this. And the other one, we will always have a solution. So in this case, we're also done. And we have proven our theorem. And this is pretty much it. But I did promise you, somewhere in the middle, that I will explain why I named this very specific structure the Golay code, the extended Golay code 324. And I can explain why I did this with a very nice picture. And this is, I think, all the space that I'm going to need. So, suppose that we have a model position. You can have any number of stars, it doesn't really matter. But what I will do now is, in this position, I'm going to start to place numbers. 0, infinity, 1, 11, 2, 2, 93, 4, 15, 15, 6, 14, 16, 17, 8, 5, 9, 21, 13, and 7 and 12. And now, in this mock position, we can equate placing stars in this diagram to adding elements of this set to a subset. So, for example, if you take the mock position right there, or one of the positions that we have done, maybe that one, because that one is actually complete, we'll get a subset 0, 15, 11, 16, 2, 10, 18, and 8. And now with this subset, what we're going to do is we're going to consider a length 24 vector. Length 24 vector with 24 elements. I'm going to place all of these digits right under it, all the way up to 22, and then at the end infinity. If in this subset we have a 0, I'm going to place a 1 here. We don't have a 1, so I'm going to place a 0 here. We do have a 2, so I'm going to place a 1 here, and I'm going to repeat this all the way up until 0. So this is 0, this is 0. This right here is actually going to be a code word of the Golay code. And the way that you can prove it is by using a counting argument. You can actually show that in this mock, there's the exact same amount of elements with the exact same amount of distributions. You can show that it's linear code, and that will pretty much equate these two with each other. So that's it.